Okay, now we're going to start looking at number systems. Number systems become important because we're going to be using digital circuits which can produce one of two states, such as highs and lows, or trues and falses, or ones or zeros. And these two states, it becomes more powerful when we can map them into a number system. So when you can start doing that, then what you can do is use digital circuits to generate, transmit, and compute arithmetic, or basically math or signal conditioning. So what we really want to do is we want to start looking at how can we map these highs and lows into a particular number system. And if we only have two states, that being a high and a low, we need to have a number system that can support only two values. So the number system that we use that has two values is known as binary. And binary, it's a simple number system, but the issue becomes our human brain has been taught to think about the world in a number system which is called decimal. And decimal has 10 symbols in it, and we count 0 up to 9, and then we go 10, 11, 12, we count up to 99 and go to 100. So what we need to do is we need to understand how to convert back and forth between a decimal number system, which is the way our brain sees the world, and a binary number system, which is how a computer operates on digital signals. So what we need to do first is study what a positional number system is in order to ultimately understand the binary number system. So we kind of define everything with respect to decimal because it's how we understand numbers. And then what we do is we take that formal definition and we apply it to other bases or other number systems, such as binary, and we'll look at a couple other ones too. And as soon as we can convert back and forth, then what we can do is we can start creating circuits that perform meaningful computations for us. Okay, so the first thing we want to start talking about is a positional number system. Now, a positional number system is one in which the position of the symbol within a number has a different value, or it has a different weight. And so, first of all, what we want to do is we want to start talking about numbers in general, okay? So when you come along, we have a decimal number system, okay? Now, decimal means that we have 10 symbols in our number set. All right. Now this makes sense. You know, we've known this since birth. But if you think about it, the symbols in this set are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there's 10 symbols. And when you define this number system, you do more than just define what the symbols are in the set. You actually define the relative value of each of these symbols. So for example, each of these symbols is greater than its predecessor by a value equal to the smallest non-zero value. So what we mean by that is that 1 is actually greater than the symbol 0 by a value of 1. And 2 is greater than the symbol 1 by a value of 1. And 3 is greater than the value of 2 by a symbol of 1, and so on and so forth. So when we define this number system, we define two things. It's the number of symbols in the set and also their relative value. So when we count, what happens is that you can think about, we start counting with the least significant symbol, and let's count in a column. So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we are out of symbols. So we have a situation where the symbols by itself are not able to allow us to count any higher than the highest symbol in the set. So what we do is we adopt a positional number system. And that means that we are going to say, okay, this will be one column or one position within a number. And what I'm going to do is I'll start counting over in this position at the least significant symbol, and what I'll do is I will bring on another higher order position in order to allow me to continue counting. So we know in decimal we go from 8, 9, then we go to 10, and then we go to 11, and then we go to 12, and then we go to 13. But if you think about what really happened is we brought on another column of numbers which allowed us to, or a column of symbols which allowed us to form a number that was larger than could be represented within the original symbol set. And it turns out that these positions can also be used to define numbers which are smaller than the smallest number in here. So we can actually use them to create numbers that are smaller than 1, and we'll see how to do that later. Okay, and so if you continue this, what happens is you get up to 91, 92, all the way up to 99. We are now out of symbols in this column and also in this position. So what we need to do is bring on yet another position, so we get to 100. But if you think about what we did is we rolled over and started counting again at our lowest symbol in this position, our lowest symbol in this position, and we had to bring on a new column. So that's kind of the way that we form our numbers. Now this is for decimal, but we extend this positional number system formation into our other number systems such as binary. Okay, so let's take a look at some definitions really quick. So one of the first definitions we have is the term radix, and that is also commonly called the base. And that's defined as it's the number of symbols in a number system. Okay. So if you say, I'm going to have a decimal number system, the term decimal means that I have 10 symbols in there. So I could say I have a radix of 10, or I could say I have a base of 10. All right. Now when we talk about a number system called binary, that means that we have 2 symbols, so that'll be radix of 2 or a base of 2. But whenever you start talking about a number system, you always start by saying what is the radix or what is the base of that number system. Okay, so from there, let's also start defining some information about this whole positional concept of a number. So let's just define a few terms. So if I came along and I had a number such as 1, 3, 2, what you notice here is that this is a number, and each number has a particular, is in a particular position. But one of the things that is missing that we can support in a decimal system is this concept of a decimal point, but it's technically actually called a radix point. Okay? And what a radix point does is it represents the position within a number where symbols to the left of that radix point are representing whole numbers, and symbols to the right of that radix point are going to be considered fractional numbers. All right. So if I had a number like 132.654, you would say, okay, these ones over here, these symbols over here are the fractional component of the number, and these numbers are the whole numbers. Now the generic term for it is a radix point. Sometimes we call it something related to the number system that it's using. So for example, if I had a decimal number system, you might call this a decimal point. Okay? But the technical term for it, or the formal term for it, is the radix point. Okay, so now what we have is, so when the decimal point or the radix point is omitted, you can assume that it is to the right of the rightmost position number. So if I just provided the number 132, there is no radix point, so what you would assume is that it would be right here, even though I can omit it. That sets the positional numbering for all of the symbols or all the numerals within this actual number. So now what we do is we want to define something which is called the position. And what we're going to do is we'll give it a variable lowercase p, and what we do here is the symbol or the position to the immediate left of the radix point has a position variable number of 0. So we say that the numeral 2 is in the 0th position. What we then do is we increment by 1 going to the left, and so the position that numeral 3 is in would be called the 1 position, or position 1, and then so on and so forth. So then this would be the position 2. So if I said, what position is the numeral 1 in, you would say, well, it's in position 2. Then what we do is we continue this going to the right, and we continue decrementing across the radix point. So numbers that were over here, such as 654, this would then have a position of -1, this would have a position of -2, and this would have a position of -3. Now this is just the formality of how to identify what position a numeral is in, but we'll see later that we can use that to actually calculate what the weight of a particular position has. So we'll say that this position carries more weight than this position, or position 2 carries more weight than position 1, and we can use that to start forming larger numbers. Okay, so some other quick terminology, and then we'll look real briefly at some number systems, the most common number systems, are we can use this concept of digit notation. So a digit refers to, in general, a digit is a particular symbol within a number. So for example, if I had our example again, I'd say 132.654. I could say that 1 is a digit. So I could say digit 3 or digit 2 or digit 5. So that's the generic term for one of these symbols. So we started saying digit once we included the symbols to form a number. Now what we can do is we can actually give it a digit notation where we have lowercase d and then we give it the subscript of its position. So I could say digit position 2 is this numeral right there, and then digit position 1 is that, digit position 0 is that, digit position -1, digit position -2, digit position -3. And we do that as just kind of a generic structure for how to name these, and we use this later once we start actually calculating or coming up with the formal calculation for the entire value of a particular number. But this is just a formality to kind of come up with some terminology and be able to address these things. Okay, so these are the definitions of how a positional number comes about, but let's look at a few of the most common number systems. So to begin with, we have decimal. We already talked about that this has a radix of 10, and it has symbols in its set from 0 up to 9, and that's it. So that we all know this radix system or this number system well, because this is how our brains have been taught to think of the real world. The next one that we really care about is binary. Now binary has a radix of 2, and the reason that a radix of 2 is important is because digital circuits only have 2 states. So they have a high or low, they have a true or false, and in this set what we're going to do is we're going to map those 2 values to 2 numbers, which are 0 and 1. So we have a binary system. It has symbols of 0 and 1, and instead of calling these digits like we do in the decimal system, what we're going to do is we're going to come up with a name called a bit. So when you say a bit, it is talking about a particular symbol within a number. So I could say bit position 2, bit position 3, or what is this bit? So when you talk about a bit, it's going to be a 0 or a 1, and it refers to the binary number system. Okay, so now one of the things that we can also look at is those are the 2 important ones. This is how our computer operates, this is how our brain thinks, and we want to be able to convert back and forth. We want to be able to understand how these numbers relate to each other. But there's some other number systems that are kind of interesting, because when you go to a binary number system, one of the things that happens is if you think about how to count in binary, you start with a 0, and then you increment it to a 1, and we're out of symbols. So then immediately what we do is we bring on the next higher order position symbol, and in this case it would be 1 here, and then we start over counting in the lower position column, or lower order position. So then we start over and we say 0, 1, and then we're immediately out of symbols again. So then what we do is we bring over a higher order here, so we bring on another higher order position, and then we start at 1, 1, 0, 0, and then we go 1, 0, 1, we start counting. This position now is out of symbols, so we go 1, 1, 0, and so we increment this higher order position, and then we go 1, 1, 0, 1, 1, 1, and we're out of symbols again. So this is how you count in binary. You go 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. You see that you quickly run out of symbols within a particular position, and you need to bring on new higher order symbols in order to make larger and larger numbers. If you continued, so you'd say 1, 0, 0, 0, 1, 0, 0, 1, etc., etc., etc. Now, when we do this, binary numbers tend to require a lot of bits in them in order to create something meaningful. If you tried to map this to, let's say, a decimal number, you could know right away that in binary over here, you would have 0, and in decimal, that would be equal to 0. Then if binary was 1, that would be equal to 1 in decimal. And if this, you got to here, you went 0, 1, this would have to equal to 2 in decimal, and this would equal to 3. Now, we're doing this just by aligning these particular rows and just knowing that that's what they would be. There is a formal definition of how you can convert from the binary code to a decimal code, and we'll look at that in base conversions. But if you just started counting, you can basically just keep counting up, and you can see that you start needing bits right away. To even to represent up to 7 decimal, you need to be able to have 3 bits, and then to go higher than 8 decimal, you need 4 bits, and you just continue and continue and continue. So then if you went to 1010, that would be equal to 10 decimal. Okay? Now, we can extend, let's see here. So now what we can do is we can actually think about this concept of we had 4 bits down here, but up here we only had 1 bit. Well, when you build a real circuit, you're never going to just have an arbitrary number of bits that scales. What you're going to do is you're going to have a fixed number of bits when you build your circuit. So in reality, if you were going to support up to 4 bits, you would actually have 4 bits in each number. Okay? So what you can do is you can add zeros to this number in binary without affecting the actual value of the number. Now, these are going to be called leading zeros. Okay? So leading zeros. And they don't affect the number at all. Now, if you have leading zeros, you also might have this concept of what we call trailing zeros. Okay? And trailing zeros are when you had a fractional number. So let's say we had like 110.001. You could put trailing zeros on a number, and they would not have any impact on the number either. So you can always put as many zeros on the front end of a number as you need, and as many zeros on the back end of a number as you need, and those are called leading zeros and trailing zeros. In a binary number system, we also have this concept of terms that describe a certain number of bits together. So we already talked about that a bit is equal to one particular column or one particular position that's either 0 or 1. If you have 4 bits together, what you call that is you call that a nibble. And if you ended up having 8 bits together, let's say you had 111000000, that then becomes a byte. And then if you continue that, you can actually, if you continued that, and let's say you had a 16-bit number, what you call that is a word. All right? And then a word, you can continue scaling that where you said if I had a 32-bit number, I would have a 32-bit word or a 64-bit word. So you have bit, nibble, byte, and word. Okay. Now, another terminology when we talk about binary numbers is sometimes we want to know, sometimes we want to call out the bit in the most significant position and the bit in the least significant position. So what we call that is the most significant position, or also the MSB, and the bit in the least significant position is called the least significant position, and that's going to be called the LSB. All right? So there's just a whole bunch of terminology that we have when we start talking about binary number systems. We have the concept of a bit, we have the concept of a nibble, a byte, and a word, and then we also have the concept of leading zeros, trailing zeros, and then we have the most significant position and the least significant position. Okay? So immediately another piece of terminology that we need to have is when we come along, we could have a number 10 and we could have a number 10, and we say, what does that mean? Well, that number, that group of symbols means a lot different things when it's in a decimal number system versus a binary number system. In binary, this was simply 2 decimal. In decimal, this was 10 decimal. So another way that you can denote what number system you're in is by putting a subscript next to it, and the subscript will tell you the base of the number. So if you saw this, it would say, oh, that's base 10. So it's 10 base 10, and this would be called 10 base 2. Now, when you see binary number systems, you don't say 10. You say 10 or 01 or 111. You don't say 111. If I had this number, you don't say 111 base 2. You say 111 base 2. Okay, so that's the terminology. All right, so that's kind of the 2 main number systems, but there's another one that's of interest to us, and that's called hexadecimal. All right, and hexadecimal is a way, it's a shorthand way to represent a lot of different bits. So for example, if I have a number like this, immediately, let's say I had 12 bits, it's very difficult to communicate to somebody that number. So you'd have to say 0000, 1111, 1111, base 2. And it takes a lot of information, it takes a lot of words, it also takes a lot of room when you're writing a computer program or you're drawing a schematic. So one of the ways that you can come up with a shorthand for this is using the hexadecimal number system. Now a hexadecimal system, or also called hex, has a radix equal to 16, and it's got 16 symbols, so it has 0, 1, it uses all the numeric symbols up to 9, and then it's out of symbols, so what it does is it takes some alphabetic characters, so then to continue and get up to its 16 symbols it uses A, B, C, D, E, and F. So those are the, that's an F, those are the 16 symbols in it. The reason this is important is because one hex symbol represents 4 bits, or nibble. So what you can do is you can start representing this where you say, okay, this would be 0 base 16, this would be equal to F base 16, this would be equal to F base 16. And so instead of saying 0000, 1111, 1111, you could say 0FF hex, and that would be a shorthand way of communicating. So we want to get familiar with converting back and forth between binary and hex, hex and decimal, decimal to hex, etc., etc. So, but remember, hexadecimal is just a shorthand way of doing it. There's also another number system which is basically just used as an example in this study, where it just shows that you can use any arbitrary base possible and convert back and forth, and that is called octal, and it has a radix of 8, and its symbols go from 0 up to 7. Now, octal is not used for anything anymore. You basically use binary and hex. You use binary for everything. Computers are built with binary. Hex is a shorthand way to communicate it. Decimal is how our brains think. And octal is just kind of a legacy thing. People used to use it for stuff, but nobody uses it anymore. Now, to wrap this up, let's take a look at, if I put this in table form, if I said, I want to take a look at what this would look like if I came along and I listed out all my number systems in a table. So, if I came along, here's the table view of these different number systems. So you can see on the left-hand side is there's going to be no leading zeros, so this is without leading zeros, but it basically gives you the cross-reference between decimal, binary, and octal, and hex. So the largest number system is hex because it can represent up to 16 numbers with one column or one position of symbols. So we basically list this, we list 16 values of hex. And then what you do is you relate that to the other number systems. So decimal obviously counts from 0 up to 15. Notice that 0 up to 15 is 16 numbers. It doesn't go to the number 16 because we use the value 0. In number systems, formally we always start counting at 0. This is how you would count in binary. You go 0, 1, 1, 0, 1, 1, and then you just keep bringing on numbers until you get all the way up to until you get to a number which is the 16th number in this count. Notice that this is where you see that F is equal to 1111 in binary. So those are things that just need to be committed to memory. Octal, just to show you the same thing, it says 0, 1, 2, 3, 4, 5, 6, 7. It runs out of symbols, starts over at 1, 0, 1, 1, and etc., etc. Again, octal is really not used. Okay, here's with leading zeros. So what's important about this is that when you have a hex symbol, it takes 4 bits no matter what. So hex 0 takes 4 bits binary. So hex 0 would be equal to 0, 0, 0, 0 in binary. Okay? And so this is a table where you pretty much need to know the first 16 binary codes for hex because we'll be interchanging, we'll be going back and forth between the two. Okay, so that wraps up positional number systems, and the next thing we'll start looking at is base conversions.